Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. So today I'll be talking about some work that actually my advisor, my former PhD advisor, Hari Balakrishnan at MIT did on rateless codes, and they're called Spinal Codes. So just before I get started, just some housekeeping notes. So you may or may not be aware that we have the website, the schedule up on the website. And all the papers, my work yesterday, the partial packet recovery, this Spinal Codes work, all these papers can be downloaded from the website. So your homework is to go to the website, read, download, and laboriously understand all the details in the papers. And I really encourage you to do that because there are more details than we have time to really go into during lecture. So with that, let's get started with rateless codes. Okay, so as many of you know, the wireless channel varies very quickly and unpredictably when you are mobile for many reasons. This is a trace that we took of walking speed mobility, and we're showing you SNR. This is a trace that Maitli Vutukuru and myself took in some previous work that we did, showing you SNR on the y-axis, sending packets to a stationary base station as a client starts walking away from that base station. And you see that we have this really rapid fading, and the channel is fading out, in and out, at timescales of just tens of milliseconds, even less than that. And these fades are really large in magnitude, more than 20 decibels of difference, and they're completely unpredictable when they're actually happening. So why does this happen? It turns out that we characterize the rate at which the channel changes by this quantity that we call the wireless coherence time. Okay, and to help you understand the wireless coherence time, let's do this simple thought experiment. Let's say that we have a transmit antenna here on the left-hand side, and we have a receiver antenna attached to a little cart moving at some velocity v to the right. Okay? And in this world, we will have just one wall and no other reflectors. So we have two paths to the receive antenna. We have that direct path of length r, and we have that reflected path bouncing off the wall. Okay? And when we're sending, we send a wireless signal at some carrier frequency, f, propagating at the speed of light, which gives us some wavelength by that well-known relation. So what we see when the cart moves at velocity v to the right is we see the superposition of two sinusoidal waves that you see on the right-hand side there. Actually, you can't see the one of the other signs. So I have a stationary sign here, which is the solid curve, the solid black curve, and that corresponds to one of the paths. And then I have another sine wave here moving, corresponds to the other path. And the signal that we receive at the receive antenna is the sum of those two sinusoids. And when you have two sinusoids moving past each other like that, you get this combination of constructive right there and destructive right there, interference in that red curve, which is the sum of the two. Okay? And if you think about this world for a minute, you'll realize that when that receive antenna goes a distance of a quarter wavelength, the path difference, the difference between the two paths, will be a half a wavelength, and will go from that constructive, from a peak to a trough, from the constructive to the destructive case. Right? So this is what we mean when we mean the coherence distance. This is the wireless channel fading in and out. So typical numbers, to put some real-world numbers to this imaginary scenario, typical numbers on this, if you're sending at a wireless LAN frequency of 2.4 gigahertz, typical, right, moving at walking speed, you'll have a coherence time that's corresponding to the coherence distance by your velocity of about 15 milliseconds. So that means that the channel will be going from a constructive to a destructive fade in just 15 milliseconds. Okay, so we knew that we've known this for a long time, right? This is basic RF theory, basic physics, modeling. And what's the typical approach to adapting to these fades? Well, there's two primary methods that Wi-Fi protocols like 802.11 use to adapt to these fades. The first one is at the modulation layer, adapting the speed that we're modulating. Right? So here I'm showing you different transmit constellations. Here's 4 QAM, where we're sending 2 bits per each of those yellow symbols you see here in this IQ plot. Right? And we know that when the signal gets received, it gets corrupted by noise and interference and fading. And so we have this metric called the signal-to-noise power ratio, where we're measuring the ratio of the 2 powers of the signal power and the noise power. And the effect we see experimentally of the signal-to-noise ratio is this spreading of the received constellation points here in red, spreading out over the IQ plane. Now, the typical receiver will look at these received red constellation points and draw these decision boundaries here that I've drawn in the dotted black lines. And the typical receiver will decide that this symbol was sent when the received constellation point is in the lower left-hand quadrant, and so on for all the other symbols. So if we have a very low signal-to-noise ratio, as you see here in the upper left-hand corner, the thing to do would be to lower the rate of the modulation, sending just 1 bit per symbol, binary phase shift keying, as you see in the upper right. This will reduce the amount of bit errors that the receiver makes. Conversely, if we have a very high SNR, we'll see the received points tightly packed in the IQ space, like this. So that means that we could go faster. We could go stepping up the modulation to 4 QAM and 16 QAM, and still make very few mistakes, crossing very few decision boundaries, even at a higher order modulation. So this is what Wi-Fi is doing, or trying to do, during these very fast fades. In the constructive parts of the propagation, when the wireless channel is very strong, it'll step up the modulation. In the destructive fading out times, it'll step down the modulation. The next thing that Wi-Fi does, in addition to varying the modulation, is varying the coding rate. Okay, so we have the modulation. This is a rough idea of the physical layer of 802.11 Wi-Fi. Right? We have the modulation and the demodulation here down at the bottom. And the modulator is taking these channel bits that are the output of a channel encoder. The message bits are coming in from above, going through the encoder, and the encoder is adding redundancy in those message bits to give us some number n of channel bits that is greater than the k message bits that came into that encoder. So, as a result, we have some fixed code rate, r, that's the ratio of k and n, and the decoder is trying to guess or infer the right channel message bits given those received channel bits. In general, the lower your code rate, r, the more parity bits you're adding to the message, the more redundancy you add to the message, and the more mistakes you can tolerate down here at the wireless layer. But, of course, the slower you go, so it's a trade-off. So that's exactly what 802.11 is doing when it's varying the bit rates. It's varying both the modulation scheme and the code rate that it uses. And here's a typical table you'll see in some product literature from 802.11 Wi-Fi vendors. So we have this scheme where we're transmitting fixed rate codes and we're transmitting fixed rate modulations. So the rate of data going across that wireless link, or the maximum rate of data, is capped. So here I'm showing you some different modulations and the throughput that each achieve at different SNR ratios. And you've probably seen very similar graphs to this before. And you'll know that BPSK is going to cap out at about 1 megabit per second. But it will be able to achieve that 1 megabit per second at a lower signal-to-noise ratio than a higher order modulations. And so on and so forth as we go up in modulation rate to QPSK, QAM16, and so on. So these bitrate adaptation protocols are aiming to stay on kind of the envelope of this curve as the signal-to-noise ratio increases by changing the modulation scheme. And the way they do that, the way they change the modulation scheme, is they have to get some feedback from the receiver. Because if you think about it, the sender just sends the bits over, and the sender doesn't know what happened, right, when the bits are received and decoded. The receiver must give some kind of feedback, at least in terms of how I've set this up, for the sender to know whether to turn up the rate or turn down the rate. And typically, in the past, how this has worked is the feedback is in the form of the presence or the absence of an ACK packet, right? So think back to Maranello yesterday, and partial packet recovery yesterday. The sender is sending over a data frame. If the receiver gets it, he acts. If not, just silence. That's the stock 802.11. And you can vary this with NACs and so on, but fundamentally it's the presence, it's a 1-bit feedback, essentially. Lots and lots of bitrate adaptation schemes, as we've talked about in the summer school, in other lectures, have been based on this method. But notice that we have latency, right? So what's the latency? What's the time between when the sender transmits and when he gets the feedback? It's the entire frame time, plus the turnaround time, plus the time to transmit and receive the ACK. And only now, only probably milliseconds, tens and hundreds of milliseconds later, does the sender have an idea of what happened on the channel, right? And the wireless channel is so quickly varying that this information may be well out of date, depending on whether the mobility is walking or stationary, depending on whether people are walking nearby, many, many factors going on here. Right. The other way that we have, that before the introduction of rateless codes, we had of assessing the right rate to use was by measuring, and other speakers have alluded to this as well. Kuhn was talking about this yesterday, measuring the signal-to-noise ratio using the preamble part of the packet. I did some work on this with Maitli in 2000 and Hari in 2009. We were using the hints from the physical layer to essentially estimate the bit error rate. But again, we have this delay. So it gives you slightly better, higher quality information on the feedback. But again, we have this delay between the sending of the data and the receiving of the feedback to tell you how to adapt next time around. Okay. So any questions I can take so far about rated adaptation before we go into rateless? Yeah, so the question was, those were modulations. Does this apply to error-correcting codes? Yes. So this is a typical error-correcting code. You're adding redundancy by adding parity bits. But you're still adding, the key point here is you're still adding redundancy at this fixed code rate, right? So you still have to play the same game of adapting that code rate in response to the channel conditions. Okay.
At the initial of the run, when the setup is being taking place between a client and a server, so what rate is being sent first? Or do they wait for some preamble modulation techniques to find out what the SNR is?
I see. So the question was, how does this get started initially when the client sends the first packet to the AP, for example? And the answer is that typically these bitrate adaptation algorithms will start at the very lowest rate, and then quickly ramp up to a high rate. So you do the sensible thing, basically. You start conservatively. Okay, so rateless codes. And this is the beautiful idea that is behind the SIGCOMM paper in 2012 that's linked from the website for Spinal Codes. Rateless codes, the idea is, at first glance, something that sounds like a really bad idea. Okay? The sender should now transmit information at a rate higher than the channel can sustain. Okay? So we're not going to try and adapt to the channel now. We're going to send impossibly fast. And the receiver is not going to be able to understand what we're the whole content of what we're sending. Right? That sounds completely broken. Right? So we have the wireless channel now varying in time, fading in and out. And say this curve here is the rate that the wireless channel could really sustain. Okay? What rateless codes are doing is sending at some higher rate that is above the best rate that the channel could possibly sustain. So we take this wireless channel, we look at it, we say, okay, we're not going to be closer to the AP than about 1 meter. That will give us a max rate that the channel can sustain, right? Because the SNR can't possibly get better than if we're 1 meter away. But we know it's going to fluctuate like crazy under that rate. And we say, okay, we're going to send at this orange rate here and completely disregard at the sender what's happening on the wireless channel. Okay? And now our difficult task, but one that they managed to solve with the spinal codes, is that the receiver is going to extract information from this very fast, dense transmission at the rate that the channel can sustain at that very instant. Okay? The receiver just is able to achieve that varying capacity and throw out this adaptation loop entirely. Okay, so that's spinal codes. We're going to talk now about how the sender works. So we're going to have to arrange for some kind of encoder algorithm to operate at the sender to send this very dense constellation. Okay? So it's not going to be a BPSK or a QPSK or a 16 QAM constellation like you saw before. It's going to be something very dense, but we don't know what it is yet. Okay, that's very high rate. And we're going to pick the bits and the constellation points that we send in a clever way so that the decoder, which has a very difficult task, I think you'll agree, the decoder has as simple a task as possible. And then we'll see how well it works. Okay, so here's the encoder, right? I'm going to take a message with big M bits. I'm going to divide my message. I'll divide my message up into chunks of k bits each. And then I'm going to have the sender and the receiver start by agreeing, and this is kind of built into the system as it ships, okay? Before it ships. The sender and the receiver have all agreed on some hash function, a random hash function, okay? And an initial state that's going to be fed into this circuit or algorithm that I'm showing you here, S naught. So we feed a random number in to the circuit on the left-hand side here, and we have the same hash function operating on each of the blocks of data. And the result is we compute this series of spines I've shown you here in blue, S1, S2, S3, where the spine is the hash of the message bits and the seed, and then the next spine is the hash of the output of the first with the next group of message bits. So notice the information flow here. Where's the information flowing? Let's think about that for a second. Okay, so these first k bits of information, those flow into all the spines because they flow into the first spine directly. The first spine's output flows into the second, and so on. So the state of one spine, you can see, depends on the message bits in that stage and all the message bits prior to that stage. So now it'll be clear that only the very last spine at the end here will have information about the entire message. Those trailing bits in the message only come into the hash function of that very last spine, S n over k. That should be a big M over k instead. Okay, so now we have our spine values, and you can think of this hash function as taking bits and a real number in and giving a real number out. Okay? A continuous number, just a real valued number. So now we need to take these real numbers and somehow send constellation points. Okay, so how do we go and do that? So we attach to each spine a random number generator. And this random number generator, it's a pseudo-random number generator, and all it does is take that spine value, S, and use that as a seed into the pseudo-random number generator. Standard computational element to generate a sequence of C-bit numbers, these X's here. And the way we send these C-bit numbers is we make passes horizontally across each of the spines. Okay? So the first set of data that we send, bits now, so we can send them on the air, is the X11, X21, X31. And then we go back to the start of the message, make another pass. But go back to the start of the message, make a third pass. Okay? So now we're striping across the message, sending information about all the bits by the time we've finished the first pass.
So X11 is C-bit number.
Yes. So far I've just told you about how to generate bits, spine-encoded bits out of the message bits. I haven't said anything about constellation points, which is what I'll tell you about next. Okay? Any questions so far up to this point?
Is it like an lookup table that happens for the scale bits using S0 and H? The output S1 is when you said it's a real number, so for a given K, I can do a lookup table, pull out a number.
So K is just the block length here. Do you mean a given message?
I'm trying to visualize this. Like, is it like for a different K, I have a value between? You said this is sort of prefixed values. There is a well-defined, predefined set of values based on the hash function. So is it like a lookup table? Like if this is the K, I know what I will be able to derive in the end, so that my reconstruction is like a reconstruction back from a lookup table.
In a sense, so yes, you can think of a hash function as a lookup table. That's true, but there are as we'll see in a second, there are exponentially many possibilities about what will come out of the hash function. So it's not like it's that easy. Yeah, there's a question over here. Yeah.
Is it that you transmit at a rate above what channel can sustain? Does it mean you are transmitting above the channel capacity in Shannon sense? Is the Shannon capacity a specific channel?
Yes. So the question is, are we the sender is transmitting at a rate above the channel, what the channel can sustain? Does that mean we're transmitting above the Shannon capacity? Yes, it is transmitting above the Shannon capacity of the channel.
Then is it like strong converse thing? Probability of error will go to 1, not only above 0, but it will drive to 1.
Okay, so you're asking, isn't it true that the sender and the receiver must make errors? Now, all Shannon says is that the communication can take place at a rate. Actually, I'll get to what Shannon says in a few slides. But to answer your question, all Shannon says is the communication can take place at that maximum rate. Shannon doesn't say that, oh, if the sender sends such and such constellation, this can't happen. Doesn't say that. So we're not violating.
There is a converse to the channel coding theorem.
Yeah.
If you go above the channel capacity, the probability of error, bit error, is bounded away from 0. Is that correct?
Okay.
That's what he's asking.
Okay, gotcha.
Strong converse also, which says not only bounded away from 0, it goes to 1.
Okay.
I think this is given.
So I think this is,
You're going to essentially send more redundant.
yeah.
Eventually be below capacity.
And also this result is probably asymptotic with respect to the block length, and we are not approaching this. So I don't think we have a violation of this here. Okay. All right, so we've gotten to the point where we're generating bits out of this message. Now let's talk about how we map that to actual constellation points to send. Right? So two simple ways that they propose to do this. The first one is a uniform mapping, where we have just a very dense constellation that we're sending. And we're basically taking the C-bit numbers. We're taking each C-bit number and mapping the first one to the in-phase x-axis of the constellation diagram, and the next C-bit number to the y-axis, the q dimension of the constellation diagram, right, uniformly. It turns out that you can also think of other mappings that are more efficient. So you might be wondering at this point, what's the best constellation shape? All right, so let's think a little bit about that. Okay, so let's start with a square constellation. And remember that the power I send when I send any symbol in this constellation, the distance of each symbol from the origin, 0 here in the middle, is going to determine the power that I'll be sending. So if I draw a circle, I'm tracing points that have the same power. Constellation points, possible constellation points that have the same power. So now let me do a kind of another thought experiment where I take points that are outside this circle and I move them in to be inside the circle. So I'm not changing the number of points that I'm sending here when I go from A to B, right? And we saw earlier that the number of points you send essentially determines the rate at which you send. So in case B here, I'm sending at the same rate. But I have moved points outside the circle to inside the circle. So I've reduced the power, on average, that I'm transmitting with in B here. This is called a shaping gain in the literature. And furthermore, the spacing between my points hasn't changed when I went from A to B. So the probability of making an error has stayed the same. So I can send at the same rate here, but I've reduced the power. So now let me equalize my power in my circular constellation with case A here in case C. So now I'm just adding points here around to equalize the power in the two cases. So now I can increase throughput. Right? So you can play these games with the shapes of constellations to increase the throughput. They chose not to in Spinal Codes. They choose usually to use a square uniform constellation just for simplicity. But it's just the observation I'm making here is that there's actually room for improvement in the way they've designed Spinal Codes. So, and as you'll see later, they get results that are very close to Shannon capacity. So it's kind of interesting that there's still room for improvement. Okay. All right, so what we'll do now is, why don't we take a 5-minute break, because we're going to have an 1.5-hour slot. So when we come back, we'll talk about the decoder and then the performance. All right, let's get started again. Yeah, question? Yeah?
So how many bits are used for the constellation? Is it 2C, CD on this side, and so on?
Yep, okay. So the question is, how many bits on the encoder side, how many bits are used for the constellation? Right, so we're taking one of the x, which is c bits, and mapping it to the I-axis, and the other x, the next x in the pass, and mapping it to the q-axis, so 2 c bits per constellation point. Yeah.
And decoder also knows about the C.
Yes, yes. So the question was, does the decoder know about the C? Yes, so all these parameters, K, the block size, the message length, C, the decoder knows about. Yeah. All right, so now let's talk about the decoder. And we'll begin by talking about maximum likelihood decoding. All right, so the way the decoder works is we have this, remember the encoder now, we have this hash function, we have our message bits, and I'm going to give you an example here that we'll stick with to simplify things. So my example is that the sender is transmitting a 1 and a 0, and that's the message, okay? And k equals 1, so my block length now is 1 bit, okay? And I have an initial seed here, and then my sender is taking my 1, hashing it to some constellation point, right? Taking the 0, hashing that to another constellation point, and those are my transmitted symbols, okay? And now let's talk about how the decoder works. So here now at the decoder, I have received symbols, which I'll denote for you by x's here. Okay? Let's just, for simplicity again, let's assume that the noise is very low, so my transmitted symbols are roughly equal to my received symbols. So now what the decoder does is, instead of inverting the hash function, which actually some people during the break asked me about, that's a hard problem. Instead of inverting the hash function, the decoder is going to replay all the possibilities of the message that was sent. Okay? So, first case, 0, 0. Right? The decoder is going to run that candidate message through the encoder again and come up with a set of replayed symbols, which I'll indicate here by the O's for you here. And it does that for all 4 possibilities. Conceptually, it does that for all possible messages that are sent. Okay? So now we have 4 possibilities of messages, only one of which is correct. So how do we decide between these 4 possible messages? What we do is we measure the total distance between the received symbols and the replayed symbols. So now here's my original picture. And you notice that if my first bit is incorrect, that'll go into the first hash function and give a result that has a large distance from the received symbol. But the observation is that now that information, that incorrect information, will flow into the next hash function. And even if I guessed the next bit correctly, I still have bad information coming on this link right here to the next hash function. And that hash function is just going to blindly compute another replayed symbol, but because I have bad information here on this link, that replayed symbol will be a large distance away. So this is the key to the decoder working so well in Spinal Codes. One incorrect guess during my replay message causes the distance to increase at the first incorrect symbol or bit that I guessed. Okay? If I guess correctly now over here, as you'd expect, everything will match up and my symbols will be on top of each other, and I'll have a very small distance. Okay? And I'm taking, for the distance, I'm taking the total distance summed across all stages in one of the passes for my received symbols. So here I guess incorrectly both times, and of course, there's no correlation between the bits coming in and the received bits, so I have a large distance. And here I guessed my first bit correctly, the second bit incorrectly, so my distance spikes up at the first bit, the second bit, because information only flows from left to right. Okay? So the takeaway message is the distance is going to jump up, increase, at the first incorrect symbol that I replay, when I replay. So now, to decide between the 4 possible messages, I sum the distance and I take the minimum distance. And in this case, with no noise, I've successfully decoded the right message. Okay? Can I answer any questions about how the decoder works?
Every time it has to go through all the possibilities, or there is some optimization?
Okay, we'll get to, the question was, does it go through all the possibilities? And not going through all the exponential possibilities is how to make this tractable, yes. So stay tuned. Yep.
Euclidean distance or the Hamming distance?
Right, so they're doing Euclidean distance here. Because we're in constellation point space, so we can compute a reasonable Euclidean distance. They can generalize these codes to work with just bits if you don't have access to the physical layer of your device, but that's not what we're talking about here. Yeah. Okay, so now we're sending and receiving one pass and trying all the possibilities. Okay, but what if the channel is really bad and there's lots of noise corrupting our signal? What will happen is we'll need to send more information. We'll need to lower the rate, okay, in order to be able to decode. So the way it does this, remember the way the encoder does this, is by making multiple passes over the same message blocks, right? So sending pass 1, pass 2, pass 3, and so on. So now at the decoder, let's think about the sensible thing to do now at the decoder side. At the decoder, now our picture looks like this, slightly different. The first pass I've drawn in red here. I've replayed symbols and received symbols. Now in my second pass, I'll have another set of symbols here in black. And they belong on the same IQ plane because they're having to do with the same data, the same output of the same hash block. So for every pass, I get a new set of replayed and received symbols. And what I'm going to do is I'm going to take the average distance. I'm going to sum up all the distances involved, both across stages and spines and down across passes. So I'll take the sum distance, sum Euclidean distance now, of all this, and everything I said before about when distance increases, when you have an incorrect guess, applies here. Okay? But the beauty of this is that as the number of passes increases, I'm more immune to noise. Because if I guessed correctly, say here, I guessed correctly, but if noise threw me off, that's going to throw off the decoding. Okay, that's going to throw off the metrics and make this correct decode less likely to be picked. So the more passes I make, the more I get to average out any bursts of noise that throw any one of these passes off the correct point. Okay? So I get this averaging out of interference and noise. Okay, so let me give you a few equations just to kind of formalize this. This is exactly the same formulation as I've shown you graphically, and you can show that this is actually a maximum likelihood decoder, what I've described graphically. So you have 2 to the n possible messages that could have possibly been sent, and you can show, theoretically, that the ML decoder minimizes the probability of error. This is picking the best, most likely point to have been sent. It's choosing the message M prime that minimizes the vector distance between the vector of all the received constellation points y and the vector of constellation points that would have been sent. That's the replayed constellation points that would have been sent if M prime were the message. And here we have just the minimization over all possible messages of the Euclidean norm of the distance of the two. So in more detail, we're taking, remember, x is the teeth constellation point sent in the Elf pass, and we're summing over all t and l for the Euclidean distance between the replayed and the received constellation points y. Okay, so now in order to limit our search, let's talk about how to think about this, this decoder in a tree structure. The observation is here for our guesses. We have 2 guesses that share the same initial bit. So let's merge these 2 guesses into some identical stage now in our thinking. And we'll do the same for the 2 stages on the right that have the initial bits of 1. Now let's take the 2 halves of the tree, and 2 halves that we saw on the previous slide, and now let's arrange this into a tree with S0 spine value 0 at the root. Okay? And the upper branch of our tree is going to correspond to going and guessing a 0 for the first bit, and we're going to hang the graph on the previous slide off that portion of the tree. The lower branch of the tree is going to correspond to guessing a 1 for the first bit. We'll do the same for the graph on the previous slide. Okay, so now what we have is a tree that has n over k levels, 1 level per spine. And every branch of this tree corresponds to guessing either a 0 or a 1 for that particular message block. And now remember, what we wanted to do was we wanted to find out the sum distance between the replayed symbols and the received symbols. So what we can do now in our tree structure is label each of the branches of the tree with that distance, the Euclidean distance between what was received and what was guessed. So now, a message corresponds to a path through the tree from the root down to some leaf. Okay, so that's a 1 and a 1 message. And the metric associated with that message corresponds to summing the values of the spines over that path. Okay, so I'm just rearranging the structure into a nice tree structure in anticipation of the next step, which is the real Spinal Codes decoder. Okay? Now, if we make multiple passes, we're going to label our branches with the sum, as you might guess, the sum over all the passes, so that a sum over a path from root to leaf computes exactly the ML metric that you saw before.
In general, you would have not just 0 or 1, but block size.
Yes, yes, that's right. So these these 0, 1 messages here are, you can think of those as the blocks, but I'm just simplifying things. Yeah. Okay. But as some of you have realized, this tree, how many leaves does it have? It has 2 to the n leaves, exponential number of leaves, right? If n is 12,000 bits, right, for a 1,500 byte message, right, then we have way too many leaves to compare. So what are we going to do about this? All right, so observe here. Think about the ML message, call that M star. And then think about some other message, M prime. And that message M prime differs only in the ith bit. So because of this prefix structure that we saw before, only symbols after that errored bit will disagree. So what that means is, the earlier the error, that errored message, the earlier the bit error that errored message has, the larger the cost of that incorrect message M prime. And the larger the cost, the less likely we are to erroneously decode M prime instead of M star. So what they observe is they can show that these runners-up, the M primes, differ only in the trailing bits of the message. So you're more likely to make errors in the last few bits of the message. So if you think about the tree, and you think about the best 100 leaves in the tree, it's likely that they'll have a common ancestor with the ML message, M star, in a small number of steps. So the strategy is, as you decode, as you go through the tree, only keep a limited number of ancestors. Let's see how they do that. So what they do is they explore the tree, but they don't go down to every single leaf. Okay? Instead, they limit their search to a beam search, meaning that at every level of the tree, they have this beam factor, B, where they say, okay, we're not going to explore more than B ancestors in the tree. And then for each member of the beam, they look ahead down to a depth D and compute the scores for every one of those children. And they call this the bubble, right? So they're looking down depth D in the bubble, and they compute the scores, which are just the metrics on the edges that we talked about before. Okay? So the algorithm, step by step, works like this. They have a beam of 2. They're going to look ahead now and expand the bubbles down one step here in the second step, B. They're going to score each of the children here. So here I'm showing you a lighter color for a better score. So these white nodes are the best. And then they're going to take this set of 8 nodes here, which are the survivors here, and sort them and discard all but 2 bubbles to enforce the beam constraint. Okay, so this bubble here has a red and a pink, so it was the worst. This bubble here up top has a red and a pink, so it was tied for worst. So they pop these 2 bubbles, and they maintain these 2 bubbles as the survivors for the next step. Okay, so rather than going down all the way to every single leaf, they just limit their search to a beam.
Is there a possibility
Okay, so
Maybe you went in the wrong direction even though it was locally correct.
no. So the question was, is there a possibility that you re-explore, you backtrack, and you go and re-explore this popped bubble at some later time? The answer is no, surprisingly. And it's surprising because you worry that the right answer might be here in this popped bubble. And if that happens, we've made a decoding error. But the argument on the previous slide was that the right answer always shares a common ancestor, is likely to share a common ancestor with all the best scoring nodes, no matter what. So it's unlikely, if you have a beam that's big enough, that you lose the correct answer in the decode. But it's possible, though.
So it's from the size of the beam. So you
Yes, yes.
probability with which this happens.
That's right, right. So when we talk about performance, keep an eye on how we pick B. But yeah, question.
Now, would this process be very prone to burst errors, particularly in the early part of the tree?
Okay, so the question was, what about burst errors in the early part of the tree? Right? So look at how look at the order in which we're sending the data, right? So if we have a burst error, what's going to happen is we're going to knock out just one pass or a fraction of a pass, right? So subsequent passes will get to average out that burst error. Okay, so we sent horizontally for a good reason. Any other questions about the decoder?
Make a comment.
Yeah.
So this exploration is something called sequential decoding that has been explored.
Yes, yes.
The decoders, the 60s and 70s when satellites were launched, they're still sending photographs.
Yes.
They're being decoded in this form because they have very long constraint length codes. So we don't know any other maximum likelihood decoding is impossible. So
Right,
we do
right.
decoding of
Yeah, so the observation was this is very similar. This is exactly the sequential decoder. It also resembles the sphere decoder as well, the breadth-first sphere decoder. I will say, though, in response to that, that the structure of the encoder, the prefix structure of the encoder, is something that I haven't seen before.
the hash function. I want to see what you have there.
Yeah?
But the interleaving is standard.
Sure,
You
sure.
want to deal with
Well,
the fates. So
right, but there's this prefix structure. Let's talk further later. But this prefix structure of the encoder, I found unique. All right, so decoder complexity. So how much computation do we save by limiting ourselves to that beam? Okay, so we're going to have. Remember, our message length is n over k. Our look ahead is d. So we have n over k minus d steps. Each step is exploring the beam nodes, right, times how many nodes our bubble expands to every time we look ahead, which is 2 to the k times d. Okay, k is the block length. I've only shown you k equals 1. So b times 2 to the d if k equals 1. And then we're going to evaluate the random number generator L times for each of the L passes that we make. Then we need to make some number of comparisons in order to select the best B candidates. So overall, we're making for the decoder, we're doing this many hashes. We're doing a number of hashes. Now let's look at this big O notation. Doing a number of hashes that is linear in the message length, n over, n, right? And we're doing a number of hashes that's exponential, but only exponential in those fixed parameters k and d. K is the block length, d is the look ahead, right? So we're exponential only in those constant, really, factors. And same story for the number of comparisons we do to choose the best survivors in each beam. Okay? So another comparison point in terms of decoders, are the low-density parity check, LDPC decoders. Those use an algorithm called belief propagation, which some of you will be familiar with. And you might be, a good question to ask here is what's the complexity comparison with these LDPC belief propagation algorithms, right? Many similarities in that they operate in iterations as well. They have the advantage of being very parallelizable, as the Spinal Codes decoder does to some extent. Difficult to give a head-to-head comparison. But in the end, the performance of Spinal Codes is quite good, as we'll see in a second. All right, so far, the only story I've told you about in how to adjust the rate of transmission, right, was to make more passes. Okay, but this has two problems. So we said that, remember the information flow in the encoder. We said that in order to transmit information about the last bits, we had to send the last symbol. So that means we have to transmit one full pass. So we're going to max out at k bits per symbol. I may be off by a factor of 2 there, but we're going to max out at some factor of k bits per symbol. So if we want to speed up that maximum rate that we can send at, we would want to increase k, but that's a non-starter because we saw before on the previous slide the decoding cost is exponential in k. We want to keep that low. So what to do? The other problem is that we have this problem of adjusting to the fine SNR of the channel. Okay? We want a finer tuning knob than simply passes. Okay? Because if we look at the rate versus SNR curve, we're going to see steps if we don't have some other story of adjusting the rate other than passes. And we're going to sacrifice capacity. We're not going to get to the maximum Shannon capacity of the channel. Okay? So the mechanism they have for introducing a finer controlled rate is this puncturing idea, which is, again, a classic idea in communication systems. The idea is, let's not send all the spines. Say we have 32 spines here. Let's not send all the spine information. Let's skip a few in between and send every 8th, for example. So now we introduce subpasses. In the first subpass, send every 8th spine, so we quickly get to the end of the message at a high rate. And now the receiver can attempt to decode before this full pass concludes. Right? So we can possibly go at a very, very high rate. In fact, if you think about it, in the extreme, right, you would just send the last spine constellation point, right? And if the channel were good enough, that would have all the information of the bits in it. So, interesting. The decoder algorithm, you can basically make trivial changes to the decoder algorithm. You can introduce a 0 score to those missing symbols, and you'll score the subpasses correctly. Right? So now we've increased the max rate if we do a puncturing of 8 to 8 times k bits per symbol. So great. And then on subsequent subpasses, we go and fill in, right, uniformly until we've reached a point where we send all the spines, and then we start a new pass afresh. And this, by the way, is kind of bringing up a point about when does the receiver attempt to decode, right? So now let's pause for a second, the physical layer, and think about framing and the link layer and all that. When should the receiver attempt to decode, right? At this point, when we send the first subpass, it can attempt to decode, and it can send a message back to the transmitter. But that will require the transmitter to pause and wait for that feedback and interrupt its forward data link transmission, right? That is wasting channel capacity, right? So actually here is a great kind of connection between the talks in the summer school. So Sachin's full duplex work, right, would allow the receiver then to, would allow the sender to not pause and the receiver to send that feedback on the reverse link, full duplex, while the sender's going. And then the sender could just stop, right? But before the full duplex work was really proven and matured, the authors of this paper, of Spinal Codes, had a MAC protocol for a half duplex sender-receiver pair to decide when the optimal pause points for waiting for feedback. That was published in Mobicom of a couple of years ago. All right, so more about the link layer. They have the standard synchronization techniques to maintain synchronization, sequence numbers for the packets. And the other thing that we see in terms of performance, and we'll see this in a second, is that a shorter message length, this is actually converse to most of the standard codes that you'll read about in the literature. A shorter message length, n, is actually more efficient. Right? This kind of makes sense if you think about the way the decoder works. Because the longer you have for a message, the more opportunity you have to lose the correct message in the decoder in a popped bubble. Right? So what they end up doing is dividing one long link layer frame into shorter code blocks and then coding over those shorter messages. All right, so how well does it work? So somebody during the break asked me about the hardware implementation, and admirably, they've gone the extra step to implement this. They did an FPGA implementation. I believe this is the block diagram of the FPGA implementation, which I'll let you look over in the paper for the most part. But at a very high level, what they have is they have, in the decoder, they're going to have worker blocks that are exploring k bits at a time and scoring each of those candidates and delivering them to a selection unit, which is selecting which of the bubbles, right, to keep and which of the bubbles to pop and discard. And then they copy that to a backtracker unit. So the backtracker unit is essentially remembering the path that the decoder took through the decoding tree, and then remembering that so that when they get to the leaf that they think is the right leaf, they can backtrack and decode the message. So they store that there. And the rest of the details I'll let you read about. Okay, so performance. So an aside about Shannon capacity. And some of this will be review for some of you, but let me say it anyway. So here's Shannon, and this was at Bell Labs just post World War II. And the question that they were thinking about back then was, what's the fastest that they can communicate bits without error over a link with some SNR? And before Shannon came along, we thought that the fastest way to do that was to send slower and slower. But what Shannon said was, no, up to some rate, we can add coding, we can do the right coding, and make the chance of error arbitrarily small. So this is the Shannon rate C that we talk about. Okay. So the codes that they were designing back in those days, we weren't very good at designing codes. So they were very far away from capacity. Okay? And so we didn't actually realize the significance of this result until we had codes that actually reached capacity. So kind of a funny circumstance where it took time for this theoretical result to be appreciated, basically. All right. Okay, so in the experiments they did, they simulated a wireless channel with two cases, both with Gaussian noise, just constant additive white Gaussian noise, and with this special type of fading called Rayleigh fading, where the channel is doing what I showed you in the beginning. It's fading in and out because of reflectors nearby. Okay? And they implemented this on that Vertex 5 FPGA on real 10 and 20 megahertz bandwidth channels. And they're looking at this quantity called the gap to capacity, the gap to Shannon capacity. Okay, so here's the picture that you should keep in mind, right? The rate here, bits I send per symbol use, is here on the y-axis, and my SNR is here on the x-axis. And my Shannon bound here is up here in red. And the gap to capacity of some scheme, some code, right, is going to be the difference at some rate of how much noise a capacity-achieving code could tolerate versus how much noise I tolerate. Okay? So if I want to go at 6 bits per symbol, my code's gap to capacity is 2 decibels. If I need an SNR of 20 decibels, whereas a Shannon achieving code would need an SNR of 18 decibels. It's my gap to capacity. Okay, so, and these questions they answer now came up before. How well are they doing against other codes, we want to know. How well are they doing against these two codes called Raptor and Strider? So Raptor codes are codes that are based on XORing random bits of data together in a clever way. And that's all I'll say about this. They're rateless. They're not rated, as I showed you before. Strider is actually work by Sachin that appeared in SIGCOMM a few years ago, and it was another type of rateless code. And then they're also evaluating against these rated codes like LDPC. This is significant because LDPC were one of the first rated codes to actually achieve very close to that Shannon capacity back in the 90s. All right, so these are basically the world-leading codes. And then how should we choose these various parameters that I talked about? Bits per chunk, beam width, number of output bits per symbol, C. Okay, so this is kind of the marquee result they have here. This is rate. This is the bits that we're communicating per channel use, per symbol we send, as a function of SNR. And here's the familiar Shannon bound here in red. Okay, so we're going from SNR of minus 5 decibels. Noise is 5 decibels stronger than our signal, all the way up to an SNR of 35 decibels. Our signal is stronger by 35 decibels than the noise. Okay, so just for to put this in perspective, typical wireless LANs are going to operate around 40 decibel max 35 or 40 decibels, all the way down to maybe a min of 5 decibels. Okay, so they're actually exceeding the region that we typically operate in wireless LANs. Okay, and they're in the spinal codes are in the blue curve here, very close to Shannon bound. Right. So what this means is that decoder is choosing the wrong bubble sufficiently rarely for them to be achieving this high rate. So that is the significant and surprising result of spinal codes. Okay. The dotted green curve here is choosing a slightly longer message length. So that blue curve was a 256-bit message. The green curve is 1024 bits. And then down here in the cyan is the envelope of what Raptor codes do. Okay? So the Raptor codes are going to be... The Raptor codes are a rateless code, and they're going to be maxing out at some rate here. And then down here, in purple here, you can't. It's hidden behind some of the curves. But down here in purple is that envelope of the LDPC curves. Okay, so each of the LDPC curves is going to be like the rated code curve I showed you at the very beginning of the talk. It's going to be going down from 0 up to some rate and then across when it maxes out at its max rate. Okay, so they've taken the envelope of how a bitrate adaptation algorithm would do with a set of rated LDPC codes. And this is significant because this is what the latest versions of 802.11n, 802.11n and 802.11ac, they both use those LDPC codes atop, with a rate adaptation algorithm atop that. Okay, so that's the rate, the best that they'll be doing. And Spinal is outdoing them. In addition, they'll have to be selecting the best rate, right, to stay on that envelope. And that doesn't always happen. Right? So another reason why this rateless approach, be it Spinal or even Raptor, would be outperforming a rated approach. Okay. The second reason that a rateless code in general is outdoing a rated code is this hedging property. And let me see if I can explain this in the 5 minutes I have left. So we said that we were operating at some constant signal-to-noise ratio, right? So the power on average of the noise is some fraction of power of average on the data. But at any particular symbol time that we send, there's going to be some amount of noise, some deterministic amount of noise impacting the channel. And it might be higher or lower than that average SNR power. This is just an average. So what that means is you have to be kind of risk averse if you're using a rated code, if you want to keep not making mistakes. If you think of the noise as a Gaussian, you have to pick a point and send it at a rate such that your decision is way to the right of the Gaussian, so that you won't make mistakes most of the time. You have to be a bit risk averse. So what they did to demonstrate this was they took the same codes, Spinal codes, and they used fixed rates. Okay? They didn't adapt the number of passes. And they plot the rate they achieve as a function of SNR. And then they took the Spinal codes rateless, the full Spinal codes, and they're well above each of their fixed rated codes. Right? So they're essentially, rateless codes get to hedge their bets on what actually happened in the wireless channel after the decode. And that's the advantage. And you see the same effect when you have an unknown fading rally channel. Okay, so now we're looking at rally channels, rally fading channels, with an average SNR with what you see on the x-axis. And they get a bit of a degradation in terms of performance, but they're still well above Strider. Okay, so how about how we choose the chunk length, right? So that was the k parameter now. So we said that the decoder is going to make b times 2 to the k operations per k bits. And remember, the decoder is trying within every chunk. The decoder is expanding the tree, the decode tree, within every chunk. So the bigger k is, the harder the decoder has to work. Right? So what they did was basically a trade-off analysis where we're trading off performance here, the fraction of capacity, the fraction of Shannon capacity that they achieve on the y-axis, versus varying k on the x-axis. It turns out they're not too sensitive, so this graph starts down here at 0.6 of Shannon, goes up to 0.9. So they're not too sensitive is the first thing to note about choice of k, and that you can basically pick a sensible value based on this trade-off. Okay. The last thing I'll talk about is sending those short messages. So again, looking at gap to capacity on the y-axis, SNR on the x. If we have a longer message, then we have more opportunities to prune that correct path. So you can see here, when the message length is 64, they're achieving a very small gap to capacity, close to 0 at low SNR. Up here at the higher SNRs, you see that gap to capacity fluctuating. So we can see that puncturing, that inability to really finely adjust the rate is hurting us. Okay, so that's all for today about spinal codes. I think the takeaway points I'd like you to think about with spinal codes is, just the surprise. I was very surprised when I saw that this scheme could come so close to Shannon capacity using such a simple encoder. That really surprised me. And actually, they've given my research group the source code to spinal codes, and my students have actually run spinal codes and verified these results. So I believe they're legit, for sure. Eliminating the need to run a bitrate adaptation algorithm and simplifying the design for better performance. So I think time for lunch now.
Any questions you want to take, or
Yeah.
maybe yeah? So few questions. It's time for a few questions before we go to lunch. Yeah.
Yeah.
The hash function which you were selecting, is it from a universal class of hash function or any other class?
Okay, so the question was, is this from a universal class of hash functions? That would be what you want theoretically. And at first they used, I think they tried to go with what that universal class of hash functions. It turns out that it didn't matter in the end so much. So the hash function itself was what was limiting the performance. It was taking up most of the computation in the decoder. So what they ended up doing was they simplified the hash function to something resembling, I don't remember exactly, this is from personal communication with them. It was something like a few XORs and maybe an add or two. Very simple. And performance still remained high. So it doesn't need to be truly random. Surprising, huh?
Yes. So to my understanding, the spine code actually have make two innovations here. One is it's a coding structure. Okay. Another is a decoding structure. So how do you see this performance gain is from this coding structure or decoding structure?
Okay, so question is like, where's the innovation? Is it in the encoder and in the decoder? So I think this is, no? Okay.
The thing is they have the two innovations, but
Yeah.
compare with which one is contribute too much
I
to
see.
their performance.
I see. So which, does the encoder or the decoder contribute more to performance? That's a good question. So I think the key structure, and this is getting back to what we were talking about before, I think the key part that's giving them the good performance is that prefix structure in the decoder that causes the metric to jump up the minute they make an incorrect guess, and then immediately that metric jumps up close to the error point, so that the bubble or the backtracking decoder, the bubble decoder, can can realize this and choose the right path. So there was a comment here that the decoder is the sequential decoder. So fair enough. So okay, but fair enough. But I think the observation, the structure of the encoder, I believe is novel. But I don't know the literature quite well enough to say that for 100% sure.
So I think on the decoding side as well, there has been some literature on tree codes in this context.
There has been some literature on tree codes with exactly this prefix structure as well. So the novelty appears to be, if I may hazard a guess, I haven't read the Spinal Code papers, so I don't know, but I'm familiar with the previous literature on tree codes and sequential decoding, having contributed to some effort myself, So the novelty appears to be on the exploration. It appears that you are essentially exploring, if you, for example, if you have a tree code, you can show that with tree codes you can achieve capacity provided you do maximum likelihood decoding. A convolutional code is essentially a tree code. Longer the constraint length, essentially your size is much larger, you will be able to get close to capacity. The problem is decoding complexity. Then they came up with this suboptimal breadth. Instead of breadth first, let's do depth and then let's backtrack.
Right.
That's the sequential decoding algorithm.
Right.
And it turns out that they actually had analyses on sequential decoding algorithm, which essentially said that when your rate is larger than capacity, you will not be able to do the decoding. Your exploration will essentially take you too long. The expected number of stages before you get to a leaf, expected number of operations before you get to a leaf, turns out to grow exponentially rather than polynomial. So there is a cutoff, and the cutoff is actually very unimaginatively called the cutoff rate. So it turns out that the complexity here is the decoding. Of course, if you explore everything, then you'll be able to get to capacity. What they seem to have optimized over here, and I think that's probably the reason why they've been able to get a little closer to capacity, perhaps than cutoff rate, is in choosing the right B. You're doing depth first, but you have enough of a breadth as well by other choice of the B. That's the guess that I would hazard.
It sounds like it's fair to say that then you could say the contribution is then the combination of using a tree encoder with a sequential decoder. And
modifying it marginally to
right,
be able to get
right.
beyond the cutoff rate.
Right.
So in that context, one other comment that I wanted to make was the right comparison is perhaps not the Shannon capacity, but the cutoff rate. Because then you know that if you do one exploration, depth first, then you know cutoff rate is going to essentially be the limiting factor. Anything above that, your explorations will be going back and forth too often.
It's a good observation.
So that's why you don't get close to capacity. You're a little away. How far away, you can essentially gauge it with respect to another parameter called the cutoff rate.
Yeah, you have a question.
What about the frequency selective channel?
What about the frequency selective capacitor channels? Do you need equalizer before that, or can
Yep.
decoder be designed?
Yep. So the question was, what about the frequency selective channels? Do they need an equalizer before that? So there was no story. I just talked about constellation points, right? So yes, if they're in a frequency selective channel, you do need an equalizer. Right now, OFDM is dominant, which is basically meaning that you'll get many constellation points on many subcarriers, and when you make a pass, you can map those to the OFDM subcarriers, which is, I believe, what they do in their implementation.
I would assume that this would work even for gray-coded constellations and all that. Is that correct, or?
I believe it would work. I seem to remember talking to them, and they had some problems with gray coding, but that is just from memory. It could be inaccurate. So since they're using a random hash function, yes, it should work. But there's, I see, you're thinking about using stock hardware, right? So other than that, there's not much reason to vary the constellation mapping function. It doesn't seem to be critical, indeed, yeah.
Okay, I guess we're done with questions. Thanks a lot, Kyle. That was an amazing presentation. We can go for lunch now.